In the last video, we talked about the integral of a bounded function over a rectangle. And let me just summarize what we did. So if you have a rectangle in Rn, okay, by the way, rectangle, again, doesn't mean, the rectangle that you're used to thinking when you think of rectangle. It's what you get when you take n closed intervals and take this direct product, so to speak. So once you have that, you can partition the rectangle into a bunch of subrectangles. And then what you do to define the integral of a bounded function is to look at two sums. One of them is the lower sum, and that's what you get when you take each subrectangle, take the smallest value of the function in the rectangle, and then multiply it by the volume of that rectangle, that value by the volume of the rectangle, and then add that quantity over all the rectangles. Then the upper sum is what you do when you take the biggest value of the function on that rectangle and then multiply by the volume and then take the sum over all the rectangles. And that's the upper sum. And then we talked about common refinements of partitions. We saw that the lower sum is always less than or equal to the upper sum, no matter what your partitions are, right? So if you take one partition and find the lower sum, and then take a totally different partition and take the upper sum, the lower sum of that partition is going to be less than or equal to the upper sum with the other partition. And then we define the lower and upper integrals to be the supremum and infimum of the lower sums and upper sums respectively. And if these lower and upper integrals are the same, then we say that f is integrable over the rectangle. And that common value is called the Riemann integral of f over q. And then we looked at an example that says that the integral doesn't exist when you have the piecewise function that 0 if x is rational and 1 if x is irrational. And the reason is because the lower sum is always 0 and the upper sum is always 1, and so the lower integral is always 0 and the upper integral is 1, and they're not the same. Okay, so here's a condition for integrability. It's called the Riemann condition. So again, we have a rectangle Q and a bounded function f. Then we have that f is integrable if and only if for every epsilon greater than 0, there exists a partition P of Q for which the difference between the upper sum and the lower sum is less than epsilon. Okay, I'll let you think about why that's true. That basically follows from the definition of the lower and upper integrals as the sup and inf of these partitions. Okay, but a proof is in the book by Munkers. But I would encourage you to write out to come up with the proof of this, because it's really not that hard to prove directly from the definition. Okay, and the proof looks more complicated than it actually is. So with that theorem, that actually can be used to prove the next theorem, which is a fairly simple statement. Every constant function is integrable. So let's say you have the function f of x equals c. This is integrable. And the integral of the function c over q is just c times the volume of q, which is what you would expect. Actually, this is pretty much trivial. Do we even need this theorem above? I don't think we do. If you just calculate the lower and upper integrals, you're just going to get c times the volume of q, because since the function is constant, the smallest and biggest value is just c, and so you get this. So, okay, this is kind of a weird statement by Munkres that this is an application of the theorem above. I don't think you need the theorem above to prove this. I mean, you could, but you don't need to. And the corollary of this theorem is that, let's say that you have Q1 through Qk, a finite collection of rectangles that covers Q, then the volume of Q is less than or equal to the sum from 1 to k of the volume of Qi. Alright, again I'm going to skip the proof, but again the proof is not very hard. I mean, if you have a rectangle like this, so let's say this is Q, and then you have a bunch of rectangles that covers Q, intuitively, of course, the volume of Q should be less than or equal to the sum of the volumes of the Qi's. Here you're just integrating one, right? So you can define a partition. Let's see. I mean, the idea is that you can get a partition of Q this way. Let's see. And then when you take the upper and lower you can take a common refinement, and then when you find the volume of Q, that's just going to be the sum of the areas of those rectangles, and that'll be less than or equal to the sum of the rectangles Qi. That's essentially the idea. Okay, maybe it takes some proof to write out the details of this, but intuitively it's okay, it's very plausible that the statement is true, and I don't think it's hard to actually come up with a formal proof of this. Okay. Now, we want to give a necessary and sufficient condition for the existence of this integral, and for that we need the notion of a set of measures 0. And so now we come to sets of measure 0. And here's the definition. So let's say that A is a subset of Rn. We say that A has measure 0 if for every epsilon greater than 0, there exists a countable covering, so a covering Q1, Q2, etc. of A by countably many rectangles such that the sum of V of Qi is less than epsilon. So if you can cover up the set with countably many rectangles, so let's say that you have A like this, maybe. If you can cover, for every epsilon, you can cover up A with a countable number of rectangles such that somehow the sum of the volumes of these rectangles, in this case the area, right? You add up the total area of these rectangles, you get less than epsilon. Okay, for every epsilon it's possible to do this, then we say that A has measure 0. Okay, let's just write down some basic facts about sets of measure 0, and I'll refer you to the book for a proof. So if you have a subset of measure 0, that subset also has measure 0. So every subset of a set of measure 0 also has measure 0. If B is a subset of A and A has measure 0, then B has measure 0. And a countable union of sets of measure 0 also has measure 0. So if A1, A2, ... is a collection of sets, this is a countable collection of sets of measure 0, then so is the union okay. And part C is kind of an alternate characterization of sets of measure 0. So we a set A has measure 0. Oops. A set A has measure 0 if and only if, for every epsilon greater than 0, there exists a countable covering of A by open rectangles this is the interior of Q1, interior of Q2, etc., such that the volume, when you sum them up, it's less than epsilon. Okay, so C is pretty much the definition, except you're looking at open rectangles instead of closed rectangles. And part D is if Q is a rectangle in Rn, and throughout these sets A are subsets of Rn. If Q is a rectangle in Rn, then the boundary has measure 0 in Rn, but Q does not. Okay, so for instance, if n is 1, then Q is this rectangle which is an interval, and then the boundary consists of these 2 points. That's the boundary of the rectangle Q. Here's your rectangle Q. This has measure 0 in R1. This has measure 0 in R. And then if you have a rectangle in R2, this is Q, then the boundary is going to be this. This set has measure 0 in R2. So, you know, you're looking at which Rn you're in. So in this first one, the boundary has measure 0 in R, and then the second one has measure 0 in R2. So Q, in the first example, is a subset of R, and in the second example, it's a subset of R2. Now we can relate the concept of measure 0 to integrability. So again, we have the same setup. We have Q, a rectangle in Rn, and a bounded function f from Q to R. Let D be the set of points of Q at which f fails to be continuous. Then the integral of f over q exists if and only if D has measure 0 in Rn. So let's just recall Q is a subset of Rn. Q is a rectangle in Rn. F is a bounded function. So if f is continuous, then f is integrable. And the only way you can relax the condition of continuity and still have an integrable function is when f is continuous except for a set of measure 0. That's what the theorem is saying. And once we have that theorem can be used to prove the following theorem. So notice that to be integrable, your function doesn't have to be differentiable, right? I mean, existence of the integral really has more to do with continuity of the function. I just wanted to make sure I'm still recording. Okay, it doesn't have to do with differentiability. Your function doesn't have to be differentiable in order to integrate it. It just needs to be continuous, except for, you know, a small set, in some sense, a really thin set, a set of measure 0. And then I'll end this video with another theorem. So suppose that you have an integrable function if f vanishes except on a set of measure 0, then the integral of f over q is 0. So let's say that you have a set q is a rectangle, say an R2, okay, and we think of something like R1, okay, some thin thing, as a set of measure 0. So you have some set of measure 0. Now this function, let's say, is 0 everywhere on this rectangle, right? So f is 0 on every point of this rectangle except for this thin purple curve, which has measure 0, then the integral of f is 0. Assuming that f is integrable in the first place. Then part B is, if f is non-negative, so I'm just going to write f greater than or equal to 0, and the integral of f over q is 0, then f vanishes except on a set of measure 0. So this theorem roughly says that sets of measure 0 don't affect the value of the integral. I mean, that's essentially what the theorem is saying, except this is stated, using precise statements. Okay. So this video was basically about basic properties of integrals, but we haven't really talked about how to calculate the integral. And the main theorem we're going to use is called Fubini's theorem. It reduces the integral to calculating a bunch of iterated integrals. And we're going to talk about Fubini's theorem in the next video. Thanks.